afternoon, everyone. Welcome to the session on Have Your Real-Time OLAP and Upsert it too. So let me briefly introduce about myself.
Just got connected to your shirt. If you're okay.
Oh, okay. Yeah, sure.
All right, let's try.
Let me briefly introduce about myself before I talk about the session. So I'm Deepthi, currently working as a software engineer at StarTree. I'm an active contributor to Apache Pinot. Apache Pinot is a real-time analytics database. And over the past 1 year, I have worked on upserts and deduplication feature and solved some of the challenges at scale. And those are the challenges I would be discussing on today. All right. So agenda for today would be, I'll be talking about OLAP systems, OLTP systems, and then I'll be giving a brief overview on Apache Pinot and its architecture, and how we built upserts in Pinot, and what are the challenges we faced as we scaled, and what are the operational level challenges, and what are the cost optimizations that we did. All right. The first part of the session, that is OLTP and OLAP, and where low latency analytics systems like Apache Pinot sits in, right? So usually we use OLTP systems for all kinds of frequent updates, transactions, CRUD operations, etc. So all the data that is stored in OLTP systems is generally in a row-level format. And it is optimized for high reliability and high consistency. For example, we have MySQL, Postgres, etc. So whereas on the other side, we have OLAP systems, which are generally used for analytics processing and stuff like that. You run all kinds of analytics queries and generate insights from them. So all kinds of large, complex queries or on that structured data is used by an OLAP system. So the examples are Google BigQuery, Amazon Redshift, etc. Now we have OLAP systems and OLTP systems. Where does real-time analytics databases sit in, right? Why do we need them? So imagine data that is constantly moving. Imagine the data that is constantly changing, where freshness matters and where latency matters. That's where real-time analytics databases sit in. And we have databases like Apache Pinot, ClickHouse, and Druid for that. So with that, today I'll be talking about Apache Pinot, right? So Apache Pinot is a real-time analytics database, which is distributed OLAP data store. So we handle all kinds of high concurrency, high throughput use cases that serves low latency queries. So the data that is stored in Apache Pinot is in columnar format, and we have all kinds of smart indexing to make that queries serve with subsequent latency. And at StarTree, we are building products that are powered by Apache Pinot to derive and generate massive amount of insights from this fast-moving real-time data. So, for example, Uber, LinkedIn, Stripe, Grab uses Apache Pinot today to power their real-time analytics. All right. With that, I want to introduce you to the core components of Apache Pinot. So first, data in Apache Pinot is on servers, and the smallest component of that data is the segment. You can imagine the segment as like a partition in any kind of a database, like a shard or a partition. And this segment is in immutable state, and all the query execution happen on a server. And then we have broker, which serves all kinds of query requests and spreads it across the servers, and servers handle all those data shuffling and all kinds of operations and brings the data back to the broker again. And all the result aggregation is done on broker. And we have controller, which is the heart of the Pinot, which handles all kinds of cluster coordination, metadata management, and state management in it. So controller consists of, again, two parts, Apache Helix and Zookeeper. Zookeeper, as you know, it's like the store which manages all the metadata for all kinds of distributed systems today. And Helix is the one that handles all the transitioning from the segments. For example, the state transitions that happen as the segments get committed to the disk and then to the deep store where the consistent copy sits in. And then we have minions, which handle all kinds of background tasks. So for example, if you want to ingest the data into Pinot using some files, CSV files, we can use minions for that. And for example, if you want to repartition the data later on, we use minions for that. For example, we have segment refresh tasks that are running in the background. All right. So with that, why do we need upserts, or what does upserts even mean, right? So upsert is nothing but you either insert a record if it's not present, or you just update the value if it's present. So why do we want upserts in Pinot? So the basic main motivation was, as the data kept changing, we wanted to capture that data and display analytics on that fast-moving data. So the use cases, for example, let's take Uber, where the trip status keeps on changing, and we want to display that status to the user as it keeps changing. So that's where upserts comes in handy. And more examples are geospatial coordinate changes, where updates keep changing, and you want to track all those updates to report the weather changes or climatic changes to the users. All right. Okay, we have upserts in many kinds of databases. Why was it so hard to build in any kind of a OLAP data store, right? Since I mentioned the segment in any OLAP's data systems, or in general OLAP systems, it's in a columnar format for various reasons, right? You can handle all those analytical queries easily. So with that format, it was hard for us to build upserts because the changes has to be done on row level. And as well, we need to maintain freshness with the real-time analytics databases. So maintaining query performance, consistency, and with no ingestion delays was very challenging. So, all right. How does other systems build upserts, right? Like not just Pinot, how did other systems build? So some other systems used to do a merge on write or merge on read as they read the data. So, or they used to merge the data in the background and display the results to the user. With this, the freshness is not that much guaranteed, and there might be delays in using such methods. Whereas in Pinot, how did we build upserts, right? What methodology we used to build upserts in Pinot? So the main concept or the main technique that we used was to make the segment mutable. Since this segment in Pinot was immutable, we wanted to make it mutable in such a way that we can make updates as fast as inserts. And we assume the data is partitioned, and primary key is the main basis point for Pinot upserts. And we had metadata management that is happening on two levels. One on server level, one on segment level. So on server level, we use it for the write path, and on the segment level, we use it for the read path. So on the server level, we have primary key to the record location, which stores the information of a segment and a document ID there. And at segment level, we keep track of which documents are current using a bitmap. We call it valid document bitmap. And this is how a read path and write path is handled by metadata. All right. Now we know we have this metadata sitting in, but how does a single write looks like, right? So when a primary key comes in, when a primary key gets ingested from streaming data sources like Kafka or Kinesis, what happens is that we look into the server level metadata map, checking if that primary key exists or not. What happens if it doesn't exist? It's like an insert. So what we do is we validate that document at segment level and insert that primary key into the server level metadata and do the insertion. Now let's say a segment 2 comes in with the same primary key that was present in segment 1. What happens here is that we invalidate the valid documents present in the segment 1 and validate the document present in segment 2 and update the server metadata in server level metadata. Now let's say segment 3 comes in with primary key 3 and primary key 4, which is already present in segment 1 and segment 2. Now the same process repeats again by invalidating the previous valid document and validating the existing document, and then updating the metadata at server level. So this is how the write path works. So on the read side, what we do is all these valid documents can be looked through as a query comes in, and we just do an AND operation on those bitmaps to display the most up-to-date and current records. All right, so we have all this metadata managing on Pinot, but where do we store that metadata, right? That might be the first question everyone would have. So that's the first challenge we face. So we used to store this metadata in memory initially, but that wasn't scaling enough. With just 500 million primary keys, we started to see ingestion lags, query latency, degradation, and each server is limited by a heap resource, right? So with that, what we introduced was to store these primary keys on disk using RocksDB. So with that support, we have increased the scale from almost 500 million to more than 5 billion primary keys today per single server, which is like 10 times, right? And the table sizes even grew from gigabyte scale to terabytes, and now we are storing in petabyte scale. All right. Okay, we solved the problem of scaling upserts, but what's the next challenge we have? The next challenge is, as I mentioned, at segment level, we have valid document bitmaps, but these valid document bitmaps are in memory. So due to that, whenever a server restarts or whenever a server shuts down, we lose all those bitmaps. And now we don't have that metadata when the server comes back up. And let's imagine you want to rebalance the servers to a server where there is no existing metadata states, right? That's when we are seeing longer restart times, longer rebalance times. So that was affecting our maintenance windows and upgrade windows. It was taking almost several hours to rebuild this metadata again. All right, that's the first challenge. And the next challenge was storage costs. Let's say the updates on a single primary key keeps on increasing, and user doesn't want that older versions of a single primary key in the server and in the segment. So with that, infrastructure costs as well grew because the number of primary keys was limited, but still the number of invalidated documents were still present in the server. So these are the main two challenges I will be discussing in the next session today, in the next part of the session today. That is, the first challenge I talked about was, the first challenge, that is, how do we reduce this restart times when you have upsert tables in Pinot? That is, we wanted to rebuild that metadata and make that process faster. So what we wanted to do was, since the bitmaps are lost, we wanted to rebuild the metadata. Even though the server level metadata was stored on disk, we wanted to erase that, make everything consistent, and rebuild this metadata again. That's the first approach we took, which is fully rebuild the metadata as server comes back up. So what we did in this approach is just look at each of the segment, iterate through each of the document, invalidate and validate the valid documents depending on which key is valid, and insert the metadata onto the server. But this process is very slow when you have billions of primary keys, petabytes of scale data. This process was slow and it was taking around several hours. All right. With that, we thought about the next approach we wanted to take. That is, since the valid documents are stored in memory, we thought, why not we store it on disk? But the challenge here was these bitmaps keep changing and gets invalidating as the incoming records come in. So we can't make it consistent, but we can still store them on disk. So what we did was, after each segment got committed onto the disk, we took a snapshot of all those segments which got updated in between and stored them on disk. So now once the server comes back up, what we did was we looked at those snapshots and inserted those valid documents into the server. The remaining segments which didn't have valid documents, bitmaps, will be reconsumed and the same upsert logic follows through again. Even though we reduced that downtime from several hours to a couple of hours, still it was a long time for the customers, right? Even though they have replicas, those replicas might be overloaded with different queries, different loads, and stuff like that. So maintaining that strict SLAs was very much needed for us. All right. The next approach or the next thought that we got into mind was we have valid documents that are stored on disk, but those are not consistent because of how we are doing it. The process wasn't consistent because of the way we are trying to take snapshots. We made that process asynchronous due to some reasons, and then we wanted to make that process of taking snapshots on disk consistent and use both metadata sitting on server and at segment level so that we can reuse these states as the server comes back up. So the main process that we followed here is on cleanup, when the server shuts down and once the ingestion is stopped, we try to persist the bitmaps on segments which are inconsistent previously, and made sure we created metadata files for all these segments and partitions so that we have a track of which segments have snapshots present or not. And then we flushed the in-memory states of RocksDB to disk and created a marker file saying, oh, this process is complete and this process is consistent now with this session. So now when the server comes back up, what we did was we checked through that marker file and see if we can reuse the existing RocksDB states that were present on segment level and as well as on server level. If not, if it's not consistent, if we don't have marker files, what we did was clean up all the RocksDB directories and use the other approaches that we had. And then we marked the server ready. All right. With that, we still had few challenges, right? What if the states were not present on a new server? Let's say we are doing a rebalance onto new servers that doesn't have existing metadata states. You can't reuse the RocksDB states there. So which is why we wanted to offload that process of rebuilding the metadata onto minions. As I mentioned before, minions are the components which we use for the background tasks. In this particular approach, that's the component that we used to periodically take the snapshots of metadata and store that metadata on deep store. And once the server comes back up, what we do is we take those snapshots, bootstrap that metadata onto the servers, and the rest of the segments which didn't generate that metadata from the time we took snapshots to the current time, we will be reconsuming that segments again and do the upsert process again. All right. With that, even in the worst case, we try to reduce the downtime of servers by almost 90%, which is from a couple of hours to minutes. But the challenge here was there was a lot of dependency on minions. Let's say minions didn't generate snapshots because some minion crashed or some error happened. We were still seeing some issues with generation of those snapshots and delta of those segments which needs to be reconsumed. And the second challenge was the resource limitations and the network latency that we have, right? Because we still need to untar all those files from the network from the deep store, which is S3 or blob store or something like that. So untarring such files took a little bit more time than reusing RocksDB states. So with that, we have all kinds of mechanisms that are built in Apache Pinot to bring back the server up even when you have lot of primary keys, lot of data that you store in Upsert tables. So let's say there is a cold start and you don't have the data. Of course, we have a solution for that, right? Like you have pre-built snapshot built already by Minion and use that for each of the partition and mark the server ready. If let's say you wanna just reuse the states, you can still do that by looking at the marker file and looking at each partition metadata, seeing if it can be reused or not. If not, we can still fall back to the way of building the metadata using pre-built snapshots by cleaning up all the states. All right. So with this, what I want to talk about is the results that we achieved, right? So with the initial approach, the recovery time of servers was taking around 5 hours. For example, there were 5 billion keys that were spread across 32 table partitions at server level. The recovery time for a single server was taking 5 hours with the initial base approach and 3 hours with the pre-built, with the valid document bitmaps that were sitting on disk, and 20 minutes with the Minion-based pre-built snapshots, and 6 minutes if we reuse the existing RocksDB states. Similarly, for 1.7 billion primary keys spread across 8 table partitions, this recovery time dropped from 3 hours to 2 hours, and then 15 minutes to 4 minutes. So now, if you want to just crash a server, if you want to restart a server, you don't have the pain of managing this metadata in Apache Pinot with Upsert tables. Now, updates are as fast as inserts, and as well as restart times were very quick. With that, I'll talk about the next part of this session, which is optimizing the costs as the updates kept on happening on these primary keys. So, as I mentioned, let's say we have a lot of updates, but very lesser number of primary keys. But even with that, the cost grew because we are still storing those invalidated documents present in each of the segment. So what we wanted to do is eliminate all those duplicated rows and display only, have valid documents stored in the Upsert tables. So what we did was we tried to merge the segments, removing all these invalidated documents and form a new segment with all the valid documents. So that way we don't need the pain of maintaining all these invalidated documents present in an Upsert table. And we also deleted the older segments as well with this. All right, we solved the problem of cost, but there was still a small challenge that we faced with these cost optimizations that we did. So we noticed that RocksDB get and put calls were a bit expensive. And with that, when we generated a lot of segments at once, when we compacted a lot of segments at once, we started to see that CPU utilization going almost to 100%. And there need to be a way to solve this, right? So obviously what we did was, since it was a background task, which was not important to the servers, we tried to limit the number of segments that needs to be generated or that needs to be updated at server level. So we tried to throttle the number of segments that gets generated and limited the number of tasks on the Minion side. And also, we try to distribute these tasks across all the partitions so that a single server or a single partition is not overloaded with too many tasks. All right. With that, I wanted to talk about the results or the achievements that we achieved through segment refresh task in Upsert tables, right? So one of the customers, they were ingesting almost 30K rows per second, and the updates rate was more than 90% on a table. With the segment refresh task, almost 2,000 segments were compacted in a single day, and we tried to save almost 2 terabytes of data per day on a table, which is like almost 80% of cost savings. All right, with that, I wanted to conclude on what I did, and I wanted to give a brief overview on what all I talked about in this session, right? So, as we built Apache Pinot for real-time analytics, we understood that Upserts is much needed and an important feature for a real-time analytics database. So we built Upserts, and then we realized some solutions weren't feasible or some solutions weren't scalable. So we tried to scale Upserts by using RocksDB as the metadata store. But then we realized that managing that metadata as server restarts was very challenging. So we tried to solve that by making the upgrades smooth and making sure we had those smart techniques as the server came back up. With that, we reduced that downtimes for the customer and made the maintenance process for Upsert tables very easy. And also, with that, we also saved the infrastructure costs for the customers by introducing tasks like segment refresh tasks. Yeah, with that, I will be concluding the session for today. So any questions, I'll be here to take upon.
So was just curious from a human perspective, when you started down this path that has these great results at the end about restart times coming down from hours and days to minutes, what were the most skeptical responses you got? Were they other technical people, or less technical people, people in your team, people outside your team? What were the kinds of we heard the technical story. I was kind of curious about the human story.
Sorry, what were the technical what?
What were the forces of change? Because not everyone would believe you could have done this when you started, and sometimes managers would be supportive. What were the forces that made this, that supported this and happening?
Oh, so the main motivation was our customers, and then the main motivation was our CEO actually, who used to push us a lot, saying, "Oh, this is not the right solution we are doing. We need to brainstorm. We need to improve this time." And the smarter way of doing that, reusing the RocksDB, which we implemented actually a couple of months ago, which we had to keep brainstorming because of all these inconsistent states that we were having in RocksDB. So yeah, I think everyone, customers, managers, engineers who built this solution from scratch, and how we scaled and then how we improved these it by overcoming these operational challenges. Yeah. Any more questions? I think I'm just before on time.